Hello everybody, I'm Saurabh Pal and I'm going to speak about mnemofs today, which is a file system that I've been developing as part of Google Summer of Code 2024 for Apache NuttX. And mnemofs is a file system that is being built specifically for NAND flashes. So what is NAND flash? It is basically a type of programmable non-volatile flash memory made out of NAND gates. So it's non-volatile, which means that the stored data remains there even after the power runs out. So why should we use NAND flash? It's because NAND flashes are very compact, they use lesser wires and thus lesser silicon and thus have a lesser cost per bit than NOR flashes. They also have a better write and erase times than NOR flash and provide a faster sequential read than NOR flash. So there are some drawbacks of NAND, most notably bad blocks. Bad blocks are blocks that are no longer fit to store data, and these blocks are not guaranteed for consistency of stored data. So NAND flashes have a high number of bad blocks right from manufacture. Also, its compact structure makes electrons act up a bit, and some of the bits may get flipped, and thus this requires the need for error correction codes. Also, NAND flash requires more standby energy than NOR flashes. So this is the layout of a NAND flash. So there's the die inside which are planes, and inside planes there are blocks inside, and inside blocks there are pages. The most important part of this is the block and the page. So let's take a closer look. This is the block and it has two areas that are divided. So one is a spare area which is there to hold metadata about the block. For example, error correction codes or bad block markers, which are basically markers that denote if the block is a bad block or not, and this is set by the manufacturer. And inside the data area there are pages. So most interestingly, the smallest readable or writable unit of a NAND flash is the page, while the smallest erasable unit of a NAND flash is the block. So why should we use a file system for NAND? uh, we want to use the storage device in a painless way, and thus we need a file system to manage storing data for us behind the scenes. So why not existing file systems? NAND flashes put forward a very unique challenge. Uh, they require out of place updates, bad block management, wear leveling. Not many file systems have these features supported, and some that do support it require a flash translation layer (FTL) to work with NAND flashes and to manage the wear and bad blocks for them. So why does NuttX need a file system for NAND flash? Uh, because NAND flashes are very good fit for storing sensor data because it costs less and it has quick writes. Also, for tinier boards, this is a very good choice for storage as it's very compact, and this compact nature enables tinier boards and thus a reduction of overall costs as well. So mnemofs is a copy on write file system that is inspired by LittleFS and a file system which attempts to solve the problems posed by NAND flashes. So this is the directory layout of mnemofs. We'll come back to this later. Let's take a look at the CTZ operation. Basically, it counts the trailing number of zeros in the binary representation of a number. So in this given number, we have 4 trailing zeros, and thus the CTZ operation gives us 4. Now, let's take a look at what is a CTZ list. So CTC lists are basically reverse skip lists with each node, say X, having CTZ X plus one number of pointers. For example, the node 2 has two pointers because CTZ2 plus 1 is 2. Uh, the first pointer of the node 2 points to 2 minus 2 to the power 0th block, which is basically block 1. Also, the second pointer of block 2 points to 2 minus 2 to the power 1 block, which is block 0. Uh, mnemofs, as you can see, has CTZ list as the on-flash representation of both the directories and the files in it. The directories contain the directory entries of the files and directories inside them. So the children of that directory, and the file CTZ list contains the file data. So let's take a quick walkthrough of mnemofs. So any changes to a CTZ list, which is file or directory, is noted down in the LRU. So least recently used cache. And then when this cache is full, it's a node is popped out of it and it's written to the journal. And when the journal is full, it's flushed onto the on flash data. So let's take a look at this in detail. Uh, the LRU is an in-memory kernel linked list with each node representing a CTZ list. So it can be a file or a directory. Uh, each node has a list of deltas as well, and these deltas are basically changes requested by the user. Uh, This LRU is a trade-off of RAM for wear reduction and is very handy in preventing repeated writes to the on-flash data. The journal is a singly linked list of blocks on the flash. It has n plus 2 number of blocks, where the first n blocks contain the logs of files and directories, while the last two nodes contain logs of the master node. So when the LRU is full, a node which belongs to a CTC list is written onto the flash, and then the new location is noted down in the journal in the form of a log. Because of the file system moving a lot of the time, the first n blocks of the journal move a lot more than the last two blocks of the journal. So the master blocks have lot less number of writes because of the LRU and the hierarchical system. Uh, so let's take a look at master node. Master node points to the root of the file system. When the root is updated, the master node is updated. Uh, this change of the master node's location is logged into the journal's last two blocks. These two blocks are called the master blocks, and there are two of them because we need backups. So let's move on to the block allocator. The block allocator gives you a page or a block when you need one. If you want a block, it skips pages to the nearest available block, and then it gives you that block. So the block allocator starts during initialization at a random block, and it sequentially allocates free pages or blocks in a cyclic manner. This is inspired from LittleFS, and the block requests are always in bulk because they are used by internal data structures of the file system, and block allocator also has a used pages list and a counter for each block to know how many pages inside each block want to be erased. So we know when to erase a block and when not to erase it. Uh, all of the erase operations happen only after the master block is updated, and thus the number of skip pages is very minimal. And this block allocator has a goal of providing a trade-off of RAM for speed. Let's move on to how bad blocks are handled by mnemofs. Bad blocks are stored as an inaccessible to the user file at the very root. Bad blocks do not occur very frequently, and thus updates to bad blocks are very rare, and so this file will not be updated very much. The bad block results from the file can be cached as well. So LittleFS uses this trick for detection of bad blocks during runtime uh, by reading the contents of a block or a page right after writing to it. So if the contents match with the written content, then it's fine. Else it's a bad block and it needs to be noted down in the bad block file. So this is all for my file system NemoFS. Thank you. And if you have any questions, I'll happy to answer them. Thank you again.